Now let's define what it means for a function to be increasing in a section and maybe decreasing in another section. A function f is increasing on an open interval I if for any two numbers x1 and x2 in that interval where x1 is less than x2, which means x1 is to the left of x2 on the x-axis, we have that f of x1 is less than f of x2. So x1 is to the left, it means it's lower. The number to the right is higher, so it's an increasing function. Maybe I'll draw a function here. Here's the x-axis. Let's do something like this. Well, we're looking for increasing. So certainly from this, let's call that C, and let's call that D. From C to D, that would be my open interval. I called it I here, but an open interval from C to D, notice that it's going uphill. So it's an increasing function from there to there, from C to D. And what that means, again, is if you take x1 there, take x2 here, that just means that x2, f of x2, is greater than f of x1 for any 2 points that you choose in this region here. And similarly, a function is decreasing on an open interval I if for any numbers x1 and x2 that are in the interval, with x1 to the left of x2 on the x-axis, it's going to be the opposite of this. I need f of x1 to be the bigger number than f of x2. So if I wanted to continue this, let's see, maybe I'll choose the point E here. So if you took the interval from D to E on the x-axis from here to here, we can see that the function is going downhill all the way. And at E is where it's transitioning back to going uphill to become increasing. So we've got increasing here, decreasing here, and then it continues increasing to the right of this. All right, one more possibility. Suppose f of x1 is equal to f of x2 for any two numbers that you choose in the interval. Well, in that case, the function would have a constant height, and that's called a constant. It's called constant on that interval. Constant on that interval. So it would be something like from here to here. Between E and F, I drew this, I shouldn't have drawn these two vertical lines. They're not part of the graph, but between E and F, it's a constant function. Has exactly the same height for any two values of x between E and F. So that's increasing, decreasing, and constant we just defined. So let's do an example where we just make it up. I'm going to do the x-axis right here. I don't need to do a y-axis, but let's just start a function that goes like this, maybe then up like that, and back down, something like that. Okay, so let's say the function is defined only between this and this. So the domain of the function would be from here to here. And maybe I'll label some of these A, and it looks like I'll put B here, and it looks like I'll put C here, and D here, and finally E there. So it's easy to find what regions on which this graph F is increasing, decreasing, and constant. So I'll put increasing, decreasing, and constant. So all we're looking for is the intervals. Let's make the biggest intervals possible. Well, between A on the x-axis and B, we can see that it's going downhill as we look at it from left to right. It's decreasing from A to B. So we could say on the interval AB, this function f is decreasing. All right, from B to C, it's increasing. And from C to D, we went back to decreasing. And then constant from D to E. I intended to make this a horizontal line parallel to the x-axis, so it would be a constant function. All of the x values between D and E have function values that are equal to each other. This negative number height right here. Okay? All right, a couple more definitions. A function f has a relative maximum, which can also be called a local maximum, at a point x equals a, if f of a is the largest value of the function when you are near a. So if we did had something like this, a function looking like this, and let's put an x-axis right there. Well, I created two relative maximums, which they frequently use the term maxima for the plural of maximum. I'm not even sure maximums is correct, but maxima means maximums. So I could put right here, f of a is the tallest point in this little tiny region right around a. F of a is bigger than f of x for any other x that's near a. So this would be a relative maximum. And there'd be a second relative maximum at this point. I don't want to call it a, but I'll call it a prime. So this picture, we have two relative maxima. And they occur at the point x equals a and x equals a prime. All right, the function f has a relative minimum or a local minimum at x equals a if f of a is the smallest value. So I could go back up to that chart, but let me make a new one where we do something like this. Well, again, I think I see a couple of relative minimum points or relative minima. This looks like one. And let's see, this one's going to be a little harder, but I'll guess it's right about there. A prime. So it's basically like the lowest point of a valley, of every valley. And the relative maximum is like the peak of the hill. Well, just a question before we end this video. How many relative maxima, remember that means relative maximums or relative minimums, can the function have? Well, there's no limit. I don't know if you remember, but from trigonometry, the graph of the sine function looks something like this. Goes on forever. That's not a very good graph. It should look a lot more uniform. But it has a relative maximum at every interval of 2 pi, has a relative minimum also. Relative minimum at every 2 pi as well. So you can have an infinite number of relative minima or relative maxima on a function.